Okay, so welcome back to the analysis of PDEs. Let me quickly review what we did before in the classes physically. In this course of analysis of PDEs, so we kind of started with the semigroup theory and applying it as a method to solve the nonlinear evolution equations. Okay. Nonlinear evolution equations, obviously with equations with linear operator. Okay. So the operator involved in them was linear actually, and we kind of went through in detail what you call the Hill-Yashida theorem and the theory of Hill-Yashida operators and the theory of acelerative operators and non-acelerative operators, and we kind of did a lot of theorems that kind of allow us to obtain local and global solutions of different nature, weak and strong, and different kind of smoothness of the solution by the semigroup method. So this was the first thing that we did actually. Then we did a set of result which kind of led us to what the so-called compactness method. Okay, compactness method. Galerkin method. So we kind of also did a good amount of theory required to make sense of this method. So and then how to apply it to solve some kind of nonlinear equations, especially reaction diffusion nonlinear equations, of the parabolic type. In which the operator may also be nonlinear. Okay, and so in other words, we kind of went through this method in detail, and we kind of applied it, and I gave you some of the exercises, some of the little projects to apply this method to a given number of PDEs or evolution equations actually. So we went into this method as well. What we would like to, what we couldn't do basically, there was another variant of the same method basically, which is essentially the same method. It's called the monotone operator method. Monotone operator method. I'm not spending, too much time on it because this is not something new. It's just a variation of a Galerkin method actually. Okay, to deal with the nonlinear evolution equation with a more sophisticated kind of nonlinear operators actually. So I'll get back to the monotone operator method, but since we have a limited time, so I would like to quickly move towards a new set of tricks that you have now solution of the nonlinear evolution equation with linear operator or with nonlinear operator, and you have that the solution is local or global, or some of the say some of the smoothness properties of it, that how much the solution is smooth actually. So all this stuff. The question is, can we ask some more questions about the solutions of the nonlinear evolution equation. So what I am basically interested in now, in our upcoming few discussions, is I would like to study, so if I have a nonlinear evolution equation with linear or nonlinear operator, and I have a global solution of it, then I would like to basically move on to a new topic, which is basically to study the long-term behavior of the solutions actually. Long-term behavior of the solutions. In other words, that what will happen to the solution as time will go to the infinity. To start with that, so we'll do basically a variety of abstract results. We will formulate very precise kind of questions. What do you mean by long-term behavior of the solutions? How to know that there is a solution for the nonlinear. There is some kind of long-term behavior for a nonlinear evolution equation. So we're going to do some of the abstract results regarding it, and we will apply those abstract results to some of the concrete equations actually, and you will be given some exercises and assignments or some projects to apply the same results to those concrete equations actually. So moving towards the long-term behavior, so I would like to start with a little motivational discussion, okay? And let me start with a very simple case of, say, a heat equation, a standard heat equation in one dimension, and a wave equation in one dimension actually. So I would like to know that what is the long-term behavior of the heat equation, the one-dimensional heat equation, linear heat equation, and linear wave equation, and why that long-term behavior of the solutions of these equations is the way it is actually. Okay, so let me formulate these two basic equations. So let's start with a 1D heat equation, say. So this is just motivation actually. Okay, so I would like to motivate you, and I would like to talk some of. I would like to keep bringing your notice some of the interesting properties of solutions of these equations, and then I would like to move to the more abstract results. So here's a standard heat equation. What do you call it? Say ut equal to k u xx, where k is a positive constant, and say the initial conditions. Say you are considering the x between 0 to pi, okay, and the time is bigger than or equal to 0, and the boundary conditions are that u at x equal to 0 and pi is 0, okay, and u at t equal to 0 is some, some initial datum actually, or some initial condition. Okay. What we know about the solution of this equation, we can solve this equation, easily by, we have several methods. So I'm not considering the abstract version. I'm considering the, the heat equation on real line actually. Okay, part of the real line. So the solution of this equation, we all know, can be found through different methods, say Fourier transform, say separation of variables, and the solution looks like something like this actually. So uxt is going to be a Fourier series, I equal to 1 to infinity, and that looks like, say, ak, some coefficient, e to the minus k square t, and sine kx actually. Okay, so this is what the solution of it, and ak is basically the 2 over pi Fourier coefficients can be computed by 2 over pi, 0 to pi, and the initial condition u naught of x and sine kx dx. Pretty much standard, everyone knows it actually. Okay. Next, I would like to put another equation on board, and that is the wave equation, pretty much standard, one-dimensional initial value problem, wave equation. So that goes like this. So utt equal to, say, a square uxx, where x is same, say between 0 to pi, okay, and the initial conditions on u at t equal to 0, say let's say the boundary conditions, let's assume that at x equal to 0 and x equal to pi are 0, and the initial condition that we have is ux equal to 0, u t equal at t equal to 0 is, say, u naught of x, and u at, say, or ut at t equal to 0 is u1 of x, actually. u1 and u2 are some kind of functions with certain assumptions actually. How does the solution of this wave equation looks like? So we all know the solution of this wave equation looks like this actually. So we know I can do the separation of variables or any other method and construct, you know, this kind of a solution actually. So k equal to 1 to infinity ak, say, cos a k t, okay, plus bk and sine a kt. Maybe must put an a here, and I can have a akx and akx here. So yeah. So the solution of this goes like this, while ak and bk are, you know, some unknown coefficients that can be determined through the initial condition. That goes like 2 by pi to 0 to pi and u naught of x and sine kx actually. And similarly we have an integral for bk that goes like 2 over a k pi, okay, and 0 to pi u1 of x and the sine a k x dx actually. So, you know, pretty much a standard solution actually of the wave equation. So here are some of the observational points that I would like to make. There are a few things that are common in both equations, and there are a few things that makes these both equations fundamentally different actually. So what are the few things that are say common? So one of the thing that is common is that if you consider the stationary version of the heat equation and the wave equation actually. So if you consider the stationary version of heat equation and wave equation, we know that this will go to 0 and this will go to 0. Okay? And you will reach to almost the same equation actually. And in both cases, the solution of the stationary problem will converge to the solution of the stationary so the both of the stationary problems are going to have a unique stationary solution actually. So a unique, in other words, these stationary equations are going to have the same unique stationary solution, and the question is, can you guess it? That solution is obviously u equal to 0 actually. Okay? In other words, that okay, if this will go to 0, you will get, if you integrate say x with respect to 2 times and apply these initial conditions, so these boundary conditions, the boundary condition will force you to get a solution that is u equal to 0. And similarly, the stationary solution to the wave equation is same that and unique, that is u equal to 0. So they both have, something in common. But there are many things which are different actually in both equations actually. Okay? So what are some of the differences? The first difference that you can observe between both equations is that in this expression, say if you take t goes to infinity, what do you think what you're going to get? For sure, you can see that in case of the heat equation, the 1D heat equation, as t goes to infinity, okay, due to this factor, the solution goes to 0 actually. In other words, the solution goes to, in long run, the solution goes to 0, and the 0 is the stationary solution basically. Okay, so the u roughly converges in time to the stationary solution 0 actually. But how about the case of the wave equation? How about the case of the wave equation? So looking at this expression, what you can say? So what immediately we can say is that as t goes to infinity, as t goes to infinity, the solution to the wave equation is going to behave like a periodic function or its composition actually. So it's not going to 0. So the u will go to converge to a periodic function, or the combination of the periodic functions actually. Okay, so that's how the u will get to 0. In other words, that in long run u will be bounded, but it does not. It's not going to go to the 0. So that's what makes one of the key thing that makes heat and wave equation different actually. Now, in other words, you can say that the heat, in long run, the u converges to an equilibrium state. Okay, so if you kind of interpret u physically, okay, kind of represents say the diffusion of a heat in the rod, okay, so that diffusion will go to an equilibrium state actually in long run. While in case of the wave equation, okay, u will not go to, or not in long run, it will not go to an equilibrium state actually. It will be in a periodic state actually. Okay, so it will be in a periodic state. So that's what makes these two equations fundamentally different. But obviously you can ask the next question, why is the case? Okay, why this is happening actually? There are several reasons for it, but one of the key reason that in heat equation u converges to an equilibrium state, while in case of the wave equation u does not goes to an equilibrium state actually. and the answer comes from the energy. So I hope you remember that what is the energy of heat equation? Okay. So what is the energy of heat equation actually? The energy of the heat equation goes like this. So it's 1 over 2, 0 to pi, okay, and u square dx actually. Okay. What we can show about this energy of the system is, I hope you have done that, how to calculate this energy of the system actually, okay, of, say, for example, heat equation. I mean, if not, I'll just give you quickly a rough sketch actually, that how you get to this energy. So this is like 1 over 2 mv square actually. So if you take mass as units, so this is really, and u kind of represents velocity, then displacement, then this is really, so this is really is the, you know, it's like equivalent of 1 over 2 mv square actually. Anyway, so this is the energy of the heat equation. I'll get into that. So what we can show about this energy of the system, okay, driven by, say, some kind of a diffusion, is that we can show that this energy over the time decreases actually. So the first thing is that energy is conserved because we have this law of conservation of energy. But what you can show as well is that the energy of the system, you know, for the case of the heat equation, decreases over the time. So therefore you're going to call that this, in this case, the energy is dissipative actually. Okay. So by dissipative, you mean that the energy decays over the time actually. Okay. So if you, while in case of the wave equation, the energy does not decay. So the system, in case of the wave equation, is non-dissipative actually. So since here the energy of the system is decaying gradually, so therefore it goes to, the u goes to an equilibrium point. While in case of the wave equation, since the energy, okay, is non-dissipative, it's constant actually, okay. So the u in long run does not goes to an equilibrium actually. Okay, so one of the key thing that makes fundamentally these two linear equations behave differently in long run depends on the energy of the system actually. And this will also play an important role in case of the wave equation actually, in case of the nonlinear evolution equations. Okay, so what is the energy of, say, the wave equation? Let me write it explicitly. Let me write it explicitly. Maybe when you kind of, so you must have encountered actually in your first PDE course this energy when you were trying to prove the uniqueness of, say, solution of the heat equation actually. Okay, so you might have encountered, okay, proving that there exists a unique solution to the heat equation, one-dimensional heat equation, over real line by energy method actually. Okay, by energy method. So similarly, the energy for the wave equation, the system driven by the wave equation goes like this actually. It's if t equal to 1 over 2, 0 to pi, and ut squared plus a squared u squared x and dx. Okay, so this is what the energy for the wave equation is. That's what we can prove is that this energy is non-dissipative actually. Okay, so it is always non-negative and a constant, a fixed or non-negative actually constant. Let me quickly. Okay, so this E is non-dissipative actually. So this is non-dissipative. Okay. Probably it would be too elementary to get into the details that how did you get this energy of the heat equation and wave equation. Maybe I can put some notes which kind of give the details of it, which can kind of recall that why the energy of the heat equation or the energy of the system driven by heat equation is this, and how we can show that it's dissipated. Maybe I show you, say quickly for heat equation and for wave equation. I put some notes actually that you can. I'll put notes on elements and that you can read it from there actually. So, okay. So what we can say, for example, do is the standard trick to show that, okay, this is the energy of the system and it dissipates over the time. In other words, its derivative is non-negative, non-positive. It's decreasing or non-increasing over the time. Okay. So here's a quick proof of this fact. The proof of it. This is not a proof of this, but it's a proof of this double star. Okay. So the proof of, say, double star. For the wave equation, I'll put notes and you can read it from there. So how you can really show it, for what you can do is that, okay, take your heat equation, ut equal to a uxx, and multiply it with u on both sides and integrate it over 0 to pi. So let's multiply, say, ut minus a uxx and say integrate it over 0 to 2 pi and with respect to, say, x. Okay, 0 to pi with respect to x actually. So what we can do with this term, so I can rewrite this term as, I hope you agree with me that we can rewrite this term as equal to, say, everything obviously equal to 0, okay, and I can rewrite this term as the time derivative of the u square and multiplied by 1/2 actually. Okay. While on other part, I can say apply, on the second term I can apply integration by parts, and I can get an expression like this actually. Okay, so I can get something like this, plus a ux squared dx and minus a ux, where x goes from 0 to x equal to pi. Okay. But since for the heat equation, u is 0 at 0 and u is also 0 at pi, so this term goes away. And you are remain with only these two terms. And now, this time derivative, so I can rewrite this as that this time, so the integral is with respect of x, and So you have this expression u square and you have a time derivative of it. So this time derivative is really independent. So this term does not depend on time. This and this term depends on the time. It contains the time derivative. So what can I do? That I can pull this time derivative out of the integral, because the integral depends on what do you call